Hello and welcome to RF Design Tutorials. This is tutorial 23 on RF microwave layout designs in ADS. This is part 2 of the tutorial series on layout designs. In the first video, we discussed about schematic to layout, layout to schematic design generation basics, and we took two case studies to go through various basics concepts. Now in this tutorial, we will go over a complete layout design of a power amplifier circuit which we designed in a couple of other tutorials we talked about in this playlist. And then we will look at how do we generate Gerber and drill file for our circuit. Now before we start, subscribe to my channel, click on the bell icon to enable all the notifications, and after you watch the video, give it a thumbs up and share it with your friends and colleagues who may be interested in watching a similar tutorial. All right, so let's go and talk about how do we approach the layout design. And at the end of this video, you would have a layout something similar to what you see on your screen right now. Now to begin our layout design, let's look at the schematic for which we have to design the layout. And this is the final power amplifier design for which we would like to go through the complete process of layout designing. And this is the power amplifier which I also talked about earlier. Now what you notice in this particular design, and again different people will do the circuit design differently. In my case, I have two sub-circuits, one for input matching network, another for output matching network. You might have designed your power amplifier so that everything is available on the same level, but it doesn't change anything, and all the basics we are going to cover is also equally valid. Now inside this matching network sub-circuit, if we push in, we can see all the transmission line based components and few capacitors which we have used. Now as discussed in the previous video, uh, if you need pad definition for this capacitor, you can always use lumped from artwork kind of components and attach the pad definition. However, in my circuit design work, I have modeled the pad definitions using these transmission line components so that I can take care of the mounting effect of these pad parasitics onto my circuit performance. And this I'm doing because I'm using a more idealistic model. But if you have more sophisticated models like from model ethics, they already include the effect of these pads. So probably your job will be a lot simpler. But again, those models don't come for free. It has to be purchased. So that's my way of doing pad parasitic calculation. Now, as this capacitor doesn't have a footprint or we don't need it because we already have it here, we can simply disable that for the layout generation. And also the two capacitors we have here can be disabled. But what I will do instead of modifying my original circuit design, which has been used in my test bench to perform all the simulation, I would make a copy of this particular schematic cell so that I can proceed with my layout design. And I can do so very simply by right clicking, copy cell. And now here I will include the hierarchy so that all the sub-circuits used in my main design are also copied. And you can see all of them have underscore V1 in front of their names. We click OK, and now we will have three new cells in our workspace window, and that's the master cell. Now, because I'm copying the finished product, I already have layout designs for the complete amplifier as well as that input matching and output matching. So I will go ahead and delete those amplifiers so that those layouts so that we start fresh from scratch. All right, so now let's take a look at your main design. And if we push inside the input side matching network, I can disable this capacitor and also these two uh, bypass capacitors. So once we do that, I do have all the components which are basically transmission line components. That means I should be able to easily create a layout out of this. And you can see all the discontinuities are modeled, all the T junctions are modeled. So I expect my layout to come absolutely proper. And let's try that. So here we will use the first technique of generate update the layout. And surely so, you can see all the layout comes out very nicely. You have the transmission line and you also have the pad for the series capacitor, which you saw, and these are all double stub matching, open circuit matching, and this is the DC bias line, and this is the series line where my gate of the device and corresponding line and stability resistor will get connected. So very simply, I came up with the layout for the input matching. Similarly, I will go and push inside output matching network. And as you can see here also, I'm using a couple of capacitors in series and a couple of capacitor as bypass. So let me disable all of them. Rest everything is very nicely set up in my schematic. So I will go ahead and generate the layout for that as well. And now you can see, of course, we also have the output matching network layout. So with this, I do have all, two critical pieces and the layout of them being generated. Now, if you have done a flattened design, that means everything is available on a single level for your circuit design and you do not have these sub-circuits, you can proceed with the process which I'm going to show you right now. But I typically prefer to keep them as sub-circuit. It makes my job easier. And also when I perform EM circuit co-simulation, I can perform separate analysis on this block, separate analysis on this block, and then using choose view for simulation, I can invoke one particular section as circuit cosim, another can be circuit. So I can mix and match and figure out where the problem might be coming from in case I see some performance degradation or criteria not being met. All right, so I have these two layout pieces. Now what we need to do for this resistor, you already know from the last video. For this resistor, I will simply change it to R underscore pad 1 so that I have the pad dimension as I explained in the last video. And I'm going to specify the pad dimension. So now everything has a footprint associated except this device because this is a power amplifier, remember, and high power devices we don't solder on the PCB but rather on the metal groove which we cut out from the PCB and we mount the device on our metal flange or the box in which we are going to assemble the amplifier. So I'm going to talk about that shortly. Now how do I go about complete layout design for this PA? Well, as we discussed during the last video, now I can use the second method here, which says place components from a schematic to layout. Again, this is one of the many ways you can do a layout. Design. I'm only showing one of the ways, typically, which is what I used when I was working as a circuit designer. All right, so here we can take our input matching, and you can see the input matching is actually flipped symbol. So when I click there and I start placing the input matching network, you can see it's kind of flipped because the DC bias line, which should have come down, you can see it's coming up. But that's not a big deal because as soon as I place it, I can mirror it around x-axis and I can click on a reference point and I can mirror my sub-circuit the way I want. See that? Pretty simple. Then the resistor, let me place a resistor in this transmission line. And again, the rubber band connectivity is actually showing you where to connect this component. So now the complete input section has already been taken care of. The only thing remaining is this pin, and I can go ahead and place that pin, which is just an easy identification. Now this device does not have any footprint, so I will not click on this device. This is the transmission line, so I'll keep it at some distance here for the moment. And again, this output matching network, as you can see, it's kindly flipped because that's my DC bias line, which is going up. Not a problem. I can always mirror it around the x-axis. And now I have the output matching network and I'm going to connect them both. It's very, very easy. So now I do have my rough pieces of the PA design. Now I only need to arrange them in a logical fashion and create the groove which I'm going to cut out of PCB, adjust this overall size of the PCB in the desired PCB area in which I want to design. So in this case, I'm going to assume I need to design a PCB in 2" by 40 mm kind of size. And again, size can be subjected as per your system requirement and how much space you have available. And just to draw the border outline, I will use this bound layer. And once I select this bound, I can select a rectangle and I can go to insert, coordinate entry, define my start point. So in my case, I will define the X start point as 0 and then Y, I would like to start from -20 because that's one of the corner. I needed Y to be plus 20. So overall it will be 40 in Y direction and I need 2 inch. So typically I'm going to specify that as 50.8. So now that's my 2 inch by 40 kind of PCB in which I would like to assemble my PA. So what I'm going to do here, I will take the input section, I will click on move and this input feed point I would like to place in the center, and as you can see the center currently is on origin because that's how I designed the overall box dimension. So I can place it at 0 0. If it is you haven't drawn the box like this, you can always click on the move icon, go to insert, coordinate entry and type in coordinates as 0 0 and it will move to that location. So not a major deal. And now here, the output section, I will just come to that shortly. Now the point is I need to mount my device in this particular slot. So how do I go about putting a groove for that device? So what do you mean by groove? Well, if you look at the data sheet of the vendor, I need to know which kind of package I'm going to use in my PCB, and accordingly I need to have a separation between input side and the output side because this device has to be fit in. So in my case, I'm assuming I'm going to use this kind of package, which is very common for PA design because you can put a screw and then put this device tightly on the flange or on the box. So if you scroll down a little bit, you can see the picture of the sample PCB, and this is what I'm mentioning. So we need to cut this groove so that we can mount this device, and you can see a couple of screws there to secure the device in place, and the gate and the drain is being soldered on the transmission line. So the question is, how do I know the size of this groove? Well, if you scroll further down and look at the device dimension given in the manufacturer's data sheet. So here you can see the width of this device is denoted by A, which is around 4.2 and the length of this device is G, which is around 14 mm. So we would like to create a groove which is on x-axis is 4.2 and the length is greater than 14 mm. So let's go ahead, and how do I create the groove? Well, the easiest thing I need to do is go to insert keep out because that groove, I don't want any routing to happen or any ground plane to be poured in that groove. That area is secured only for the device or as a marking line for cutout. So I'm going to use insert cutout, draw it on con layer, and I will choose a rectangle shape. And again, you can either do the freehand drawing or you can insert a coordinate entry. So in this case, what I'm going to do is insert a coordinate entry, select my first point as 0 0 because I just need a start point, and X I know is around 4.2 and if you want to keep some margin, you can of course give a margin, let's say 0.2 100 micron on either side, so that your device can easily fit in, but again it's your choice. The Y dimension was 14 so I'm going to keep some extra margin, so I'm going to keep it as 16 and when I say apply, you can notice I do have a cutout rectangle here. And this keep out by default will not be selectable. But what I have done here under options preferences, I have made keep out as a selectable object. And that's why I'm able to select it. All right, so now I'm going to take the midpoint of this keep out and align that midpoint to this input line, and that's where the drain of the device is going to get gate of the device is going to get soldered, and that's pretty much like how your schematic design is. As you can see, the gate of the device is going to land on this pad. And again, when we were placing components from schematic to layout, you see we left out some components, and that's why they are marked as highlighted. So what we can do here, go to layout and say clear highlighted components so that it's taken away. All right, so pretty simple, nothing complicated. All right, so now once we have our groove, now we know how to position this output matching. And again, I can move this train lead component and I can place it at the midpoint again. So now things are nicely aligned and you have the keep out and everything. Now notice here on the x-axis, you are pretty much meeting the board guideline. You have little bit of delta, so that's not a problem because usually your SMA lead will come on top of it. But in case you want to meet outline, you can always add a little bit of delta to align the edge with this board outline edge. But keeping 100 micron offset is always helpful so that you still have some cutting tolerance when you cut this PCB. All right, so another thing which you notice, the bias line for both drain and gate are going outside this board area, so that's not good. And also the way they are drawn, it's not a best utilization of the area available. So I would like to bend this line, I would like to adjust this line. Now when you do that, you have a couple of options to take care of this. One is, remember, this is a hierarchical sub-circuit of input and this is hierarchical sub-circuit of output matching. So I can select the hierarchy. I can push inside the hierarchy by using that button. And now here I can modify this length or this line and I can rotate it the way I want. That's option number one. And how do you rotate this line is very, very simple. So I'm going to show you both the variants. I'm going to modify the input transmission line inside the input matching network. Okay, so once I select this line and if this info button is switched on, if info window is not visible for you, you can right click anywhere here and switch on the info. So that shows you the property of that transmission line. Otherwise, you can always double click and look at the property. So I'm going to replace a line which is 0.37 mm in width and 19.7 mm in length. And that line can be drawn using the transmission line elements which you have available here. Or you could do a freehand drawing using trace like I showed you during the last video. So let's click on trace, enter the width as 0.37, and I'm going to use end style as truncate and corner as a square. Right, so once I do that, I can start drawing my trace anywhere in my design. And as you can see, when you move your mouse, you have the readout changing. So I would like to go to dy of -5, which is length of 5 mm. And then I will put the tension towards slightly left hand side and I can stretch my line somewhere closer to 13.6 and then 17 or 18 kind of and finally I can turn this line back on this side. So I will go with 19.7 because our grid precision right now is 0.1 so everything is snapping to grid because this grid snap is switched on. And under option preferences, you can set the grid snap distance to 0.1 mm. And that's why I was able to achieve this line. Now, once I have the equivalent line with the same width and length, I can simply delete that line and insert this line here. So imagine what will happen now. Now the relationship between your schematic and layout got broken because this line does not exist in your schematic, right? So once I insert a trace, if I want that relationship to hold good, I can take that line and as we discussed in the last video, I can right click, path trace, I can convert the trace and convert it to microstrip line and insert any discontinuity models. So now I have switched off the text actually. So if you switch on silk screen, you can see the trace has been converted with a equivalent microstrip line. And this was the pin which was connected and this is pin 3. So I would like to connect the same pin again at exactly the same location. Now, if needed, if you want to maintain the consistency between schematic and layout, I can go ahead and generate update layout and this will go ahead and update the layout. And notice when you do that, slide connections will be broken because these components were disabled when we originally did the analysis, but that's not a major problem because there are only a couple of components like that, and we can easily get it back. So this components or this capacitors can be again placed at the end of this overall transmission line, and now I can go ahead and make that connection here along with rest of the line, so that when you activate these components for your circuit simulation, you have the right result. Sometime using this method, be careful if you end up simulating this circuit with these capacitor disabled, especially the series ones, then you might have an open circuit issue. So make sure you enable that after you have done the layout generation. So this way your input matching network also is updated, and if you want, you can go to your main amplifier design, simulated ones, just to make sure no adverse effect has happened due to the line bending and you inserting multiple sections. All right, so that's one way of doing it. So similarly, how I did here, I can go to the output matching network. So I will push out of this hierarchy. I can also go inside this output matching network and do the same thing. The another way is, in case you don't care about maintaining consistency between your final amplifier layout and the preceding sections, there's another way. Instead of going inside this subnetwork and modifying the objects, I could simply flatten this subcircuit here. I could right click, component, flatten, and I will flatten one level of hierarchy, not all level. If I flatten all levels, then everything will become polygon or rectangle and things like that. So I will go ahead and flatten one level of hierarchy. And now what it does, it exposes all the component in your top design. But again, be aware that now your main amplifier's layout design and corresponding schematic design will not be 1:1, because you just broken down this hierarchy. So essentially what it means, you have gone in, you have taken all these components and removed that components from the hierarchy, and you have placed it in a main design, something like this. So now this does not exist in your actual layout. This is the structure which you have. All right. So what I did was just for explanation, but this is just to let you know that all the things from inside is gone because that hierarchy is broken. And now all the components which were below that hierarchy is now available at this level of your circuit design, and which is what you see here. So this is still a hierarchy block, but all these components are now available on the main PA layout design. So again, different people have different preferences. So I've shown you both the way, whichever suits you. Now this line, which I wanted to convert, is 1.32 mm in width and 18.3 mm in length. So very quickly, we can go here, change it to 1.32 mm, corner square, truncate, and I can start drawing some line like around 9 mm or 10 mm approximately, whatever you prefer. And then we will go to 18.3 mm and simply draw that line. Remove this line and connect this. Now, if your purpose is only to do EM simulation, you can leave it as trace. But in case you eventually want to, create a final, PA schematic, which is equivalent of this layout, you can go ahead and again do the same thing. We can go to part trace, convert traces, microstrip, click OK. And now you can see all these things have been converted to microstrip equivalent. So the choice is yours. Now, once I have it here, I also have this long short circuit stub, which is actually occupying a lot of area here. And here I would like to do some ground pouring. I would like to write my text on the PCB, my name, circuit name, and all that. So we can even bend that. So it's 0.89 mm and 14.4 mm is the length. So I can take this trace again, 0.89 mm. And now I will draw the line, something like 6 mm, and then finally I'm going to stretch it to 14.4, and we are done. We'll remove this stub and connect the trace here. Now, whenever you are bending traces so that you create this kind of parallel segments, take care of keeping this distance as more than 5 times the substrate height. Okay, and substrate means your signal to ground layer separation if you are dealing in multi-layer PCB. That will not have any serious parasitic coupling. If you keep this line too close and make it like a small vertical segment and a long horizontal segment, you might introduce some undesired coupling. So always remember 5H is the good thumb rule to use. So now we have our short circuit stub, we have our line bends. You can see everything is nicely filled up. I will add one more keep out, and I will add that keep out, somewhere here, and that is the region I would like to put my text. All right, and again, I have barred any plane interfering into my keep out or any kind of routing in case you're doing any additional routing on the board. So nothing will go inside this keep out. Right, so once the keep out is here, I would like to write some text. So go to parts and I can use the block text font library. And I do have different type of fonts. You can pick whatever you need. So I will call here a demo PA example. And when I click apply, you can see a small text with my mouse. I can change the height or the size of the text by putting any different number. So put a demo a PA example, and again uh, design for the training tutorial. So whatever name you want to give, your company name, your design name, or whatever. And now I will change this size of the text a little bit, and here. So I have everything included, whatever I wanted in my final PCB. So let's quickly do a ground pouring. So I'll go to insert plane. I'm going to insert a plane on con layer. That's the layer I have been drawing. I can define the clearance here, or it could pick up clearance from the rules which you might have defined in the constraints manager. But just before we go to plane, remember when we fabricate this kind of PCB, we might need to do some tuning, right? Because sometimes due to tolerance of components, due to the data sheet and model, nonlinear model difference of the transistor, our performance might shift a little bit, or even with the PCB tolerances, either fabrication or dielectric constant, etc. So we may need some flexibility to tune these kind of devices or circuits after production. So in that case, what I'm going to do is the concept which we typically use, and that you can even see in the demo layout design which vendor has provided. Notice what they are doing. Small rectangles along the RF signal path wherever you need, and if you're using any open circuit stub, even the ends of that stub could have those kind of stubs. So these things will help you do post-production tuning, because you can place a copper ribbon or a copper wire across these and try to alter the impedance of the line in order to tune the performance or the shift you have. So same thing I did in my actual layout, and here I can simply copy the portion of these. So you already know how to draw these rectangles. I don't need to teach you. And those rectangles I can push inside this hierarchy, and I can place it, because remember that design is something which I'm not ready to flatten for some reason, just as a just to show you as a variety. And again, you can keep a few things here. Either for a stub, you can either keep the small rectangles, or you can keep a rectangle equal to this width. Is all your choice. All right, so let me delete some of them. And again, I want this to happen across the length. So I'll also copy paste. And same thing you could do here. You can keep a couple of rectangles against that stub. Right. So now at least you will have some flexibility of changing the impedance of these lines, and effectively you know what you're changing inductance and capacitance and so on. So anyway, so once we place there, same thing we could do here, and it only makes sense to have it in RF path, so there is no point keeping it anywhere else. So we can define it all across the RF path, and also rotate and place it along the width of this stub in case we feel we might need some more capacitance. So by widening this line, I will have some more capacitance and things like that. All right, so anything which you want to do, you can go ahead and do it first. Anticipate what you might end up needing at the after the fabrication to correct the performance. And finally, I need a placeholder because I need to mount the bypass capacitors, and I need a place to solder my bias line if I'm going to use the feed through to provide the power. If you're going to use a connector on your PCB, something what's shown here, for example, you can have a footprint of that connector so that you can provide the gate bias and the drain bias connection. But sometimes people assemble it differently. And again, because this is a hierarchical circuit, I need to go inside. Now I can put out this port a little bit here. And now I can insert either a rectangle or a new trace or a simple transmission line. Now, because this, every time I want to make sure my schematic is always updated, I would go ahead and use a transmission line microstrip library. Take a MLIN, maybe 0.6 mm length and a 2.5 mm, which is kind of sufficient to mount two shunt capacitors, and then a small pad with 2 mm, maybe 2 mm by 2 mm, which will help me to mount the DC connection point. And again, I can take and put this port here. And if needed, I can go ahead and generate the update schematic once again, which I'm not doing right now, but you can definitely do that. All right, so output has been modified. Similarly, I could actually copy paste these two guys here, Control C, and I can place it on the baseline here. Pretty simple, nothing complicated. Now let's go ahead and insert our plane. So we go to insert plane and define the clearance as 0.5 mm or whatever you prefer by your own design rule. And we design a rectangle by clicking on these two extends, and now you can see nicely the copper has been poured. Now how to go about putting the ground stitching vias, not a problem. So for ground stitching via, if we look at the stack up, I have used whole layer, and I would like to use the same layer as used in my stack up, because later after your final layout is prepared, you obviously would like to do EM circuit co-simulation to take care of all these practical line effects. So I would use the same layer whole. And now using the whole layer as an active layer, I can draw a rectangle. Just click and draw any rough rectangle. Circle. Click on that circle, and you look at the radius in the properties window. Again, if this window is not there, right click and switch on properties. Now here I can enter the radius I want. So in this case, I'm going ahead with 0.1 mm radius, so 1 mm diameter. So once one hole is drawn, I can always go and select edit, copy paste, step and repeat. And now I can declare how many rows I want. So for example, I need 3 rows, I need 10 columns, and now it will create an array instance, as you can see. So with this array instance, I can place it anywhere in my design as I want, and very quickly create an array of the VM. And this is flexible. If you need to reduce number of columns, you can go 5, or even reduce it to something like 3, for example, and then place the via holes wherever you deem necessary to provide the best possible shorts to your layout. And in this case, I will go ahead and do row by 2, and now I can place this via here wherever required. Right, so this is to ensure that you have the best possible ground stitching in your PCB as available. So final decision is your how many holes you need. Now once you place the hole, you can notice a couple of things. One, the short circuit stub is still not connected to ground, and that's a very dangerous mistake because it's a short circuit stub, remember? So these small things have to be taken care of. So while I'm on con layer, I can simply draw a rectangle which kind of shorts this stub with the ground plane, and when that happens, you can see the hatch pattern on this rectangle as well as these vias, because this is a ground net, and that ground net is not the same name as you have drawn for the rectangle or the via. So I can click on this blue dot. It will ask me to merge, and if I say OK, you can see everything is gone, and now this becomes ground net, which is good. Similarly, for the via, select any one via of the array, click on this blue dot, click yes, and now all the vias are now part of ground net because they are all shorting vias. Sounds good? All right, so with this, we have our final PCB for the PA. Now the question is, how do I load it for manufacturing? So obviously you will need to generate a Gerber file, and that can be very simply done by going to File, Export, choose the format, what you want. So Gerber drill, DXF, GDS, there are many variety of file formats, but Gerber drill is the most common. So I'll select Gerber grill and click on View File after export. Click on more options and you can select the options as given to you by your fab house and select the layers which you want to export. So bound layer is my outline layer. I necessarily don't need to have it in Gerber, but in case your PCB fab house wants you to give an outline, you can select that. And also you can choose positive or negative polarity in the Gerber file generated. Under drill, right now I have only one layer used to draw the drill hole, which is hole, and all vias have the same diameter of 1 mm, and that's what you see. If you have multiple diameters, different layers of hole, all that will appear here, and this information will go to your drill file. Click OK, and I already selected view file after export, so once you click OK, the Gerber file will be generated, and then you will have a Gerber viewer showing you the complete Gerber file out of your design. And by going to layer table, you can switch on and switch off whatever layer you want to see in your Gerber file. Now, where are those files on your hard disk? Well, if you go to areas, a main window, right click on the workspace name and explore it in Files System. You will notice under your workspace, a new folder got generated called MFG, which is manufacturing. And inside that folder, you can see your cell name, and that's the design you were working on. Double click, and now you have a Gerber and you have all the files here. In case you want to open any file to look at the content, feel free to edit it over using WordPad. And this is a drill file, an NC drill file as we call it. And you can see all the content of the file. All right, so with this, we come back to our agenda and we did cover all the topics which we were hoping to cover in this tutorial. I seriously hope you like the content presented, and this video will help you doing your layout designs of complex circuits such as power amplifiers, mixers, oscillators with much greater ease with all the tips and tricks you learn in this video. So again, don't forget to like the video and share your comments in the comment section below this video. Give it a thumbs up and share it with your friends and colleagues to make sure everybody gets benefited from this free learning. Thanks a lot for staying till the end and wish you a happy designing.